Yesterday we talked about section 5.2. We talked about identities. What we're going to do in section 5.2 today is talk about solving. And this is going to flow right nicely from what we had been talking about in chapter 4. This is like a direct extension of what we had been talking about in chapter 4, and then starts to feed into what we've been talking about in chapter 5 with the identities. So it just kind of like melds right in there in a pretty righteous way, which is fun, right? Like, you love it when everything just starts overlapping all the other things you've done all year and it becomes like one big alphabet soup of confusion. I say alphabet soup because there's all the letters and stuff in math, right? I'm hoping it's not so confusing. Okay. So, recall, if we want the exact value of sine inverse of 1/2. This was something we would have done in the previous chapter, in chapter 4, right? Everybody's good with that? So to do this, we note that like the fundamental range for sine inverse goes from negative pi over 2 to positive pi over 2. So we're talking about quadrants 1 and 4. Inside of quadrants 1 or 4, we know sine is positive only in the first quadrant. So we're talking about this angle here, which is a positive angle. So I can go directly to my unit circle and read off the value pi over 6. Everybody cool? Let's contrast this with finding the exact value of sine theta equals 1/2. So the previous question had just one answer, right? Pi over 6. How many answers does this question have? More than 2. Infinitely many. Yeah, right? Like, yuck. Why is there infinitely many?
Because there are infinitely many.
Right. Well, certainly, like, we know that one solution is pi over 6, for sure, right, from the previous one. But so would, if you added 2 pi to this, so would 13 pi over 6 be an answer?
Yes.
Right? And if we added 2 pi again, that would be an answer. Or if we subtracted 2 pi, that would be an answer. Gaga goo goo. That's a lot of answers. And that's not even all of the answers. Right? If I look at the unit circle, is pi over 6 the only place on the unit circle where sine is equal to positive 1/2? Nah, right? There's another spot. The other spot is 5 pi over 6, which again, anything coterminal to that would also be a feasible solution. So like 17 pi over 6 and 19 pi over 6, or negative 7 pi over 6. So what do I do? Well, this is the way that we do. This is the way we're going to do it. So what we're going to say is we're going to say, okay, pi over 6 is an answer. And then we're going to say everything coterminal to it is also going to be okay. So by writing plus 2 pi times n, where n is a integer, you're talking about any multiple of 2 pi, right? Any whole number multiple of 2 pi. And because integers can be positive or negative, I'm getting adding 2 pi and subtracting 2 pi's. Is everybody cool with that? So I'm just going to tack that onto the end. And that's what I'm going to say is my answer. So that's how we're going to represent our infinitely many answers. I have 2 fundamental answers, pi over 6 and 5 pi over 6. And then I have everything coterminal to those ones. That's the way we'll write that. Which is much better than trying to list infinitely many angles, because you'd be at that a while. Is everybody okay with that idea? Okay. What if we had asked you to, again, we're going to find the exact values that satisfy this equation. On the interval from 0 to 2 pi. So here, depending on what that interval is, can we have more than one answer?
Yes.
Yeah. In fact, if my interval is 2 pi long, should I be expecting more than one answer? Yes. Right? If you're more than one full time around, you're going to run into that value more than once on the unit circle, right? So because 1/2 is a unit circle value, I can just go to the unit circle and pull the places where sine has the value of 1/2. Those are the only places where that happens. So I have 2 answers. What if we had changed this to be, say, what if we wanted everything between negative 3 pi over 2 to 7 pi over 2? Well, what I'm going to do is I'm going to use our infinitely many answer. And I'm just going to take each one of those answers, keep adding and subtracting 2 pi as long as we're inside the interval, right? So if I take pi over 6, if I add 2 pi to that, I get 13 pi over 6. That's still less than 7 pi because that's 3.5, right? And that's like 2 1/6. Everybody's good? If I add another 2 pi to that, it's going to be too big, right? That's too big. So I don't want that one. If I subtracted 2 pi, that is like negative 2 5/6. That's negative 1.5 pi. That's too small. So I don't want that one either. Then I'm going to do the same thing with 5 pi over 6. Right? So that's going to be 17 pi over 6. That's okay. right? 3 and 8, or 2 and 5/6. So that's okay. If I do it again, though, that's too big, right? That's over 4. Agreed? And if I subtract 2 pi, that's going to be negative 7 pi over 6. So negative 1 and 1/6, which is okay. That's still bigger than negative 1.5. But if I subtract again, that's way too small. That's negative 3 something. We okay with what I did there? That's usually the easiest way to do it if you have like a kooky interval, is just find the infinite answer and then just keep adding and subtracting until you find stuff that's not inside the interval anymore. What do you guys say to that? Is that okay? Let's try another one that's not based on the same stupid problem here. Yes, Blake.
Okay, so this is more of a general question, not so much applicable to this, but if we were, so you said that you would take points off if we did not include a variable. Is that only in the final answer, or do we have to have the variable in all steps?
Whoa, so you're talking back from 5.1. I want to see that variable all the time. Anytime you write down, if I see if I see like cosine equals 2, I'm marking something wrong.
Okay, and so
now there might be a cap in terms of like, okay, you did it on this problem, whether you did it 1 time or 10 times, might be the same amount off. Like there won't be, it's not like each time you do it is more per se, but like if you do it on all the problems, I'm not taking a little off from each of them. But if it's like you can't get like 0 points on a problem where the only thing you did was forget the variables.
Okay.
You know what I mean? Like,
and also,
even if you did it on every single step.
So let's just say it's like, because there's like some other weird symbols, like the weird U and then the beta.
Yeah.
Can I just simplify that to X?
Oh, I hate that too, but I won't mark it wrong.
Cool. Good to know. Good to know.
Okay.
Yeah, that's it. I was just wondering.
So Blake's working on the homework right now. He's just announced to everybody.
Yeah.
Which is fine, I guess. Back to our example, though, on topic here. So let's say we have cosine squared x is equal to 1, and we want to find our answers between 0 and 2 pi. Can I do cosine inverse to both sides of this right now as it's written? No. Why not? The squared, right? Everybody's okay with that? What do I got to do before I can do cosine inverses? Get rid of the squared. We'll take the square root both sides. Yeah. When I square root both sides of an equation, what happens? Plus or minus. So this is going to break up into 2 equations. Cosine x equals -1, and cosine x is equal to +1. Very cool. So for the first equation, I'm going to be looking up on the unit circle where cosine inverse is equal to -1. So if I go look at my unit circle, I guess I should drop one into this lesson here so I don't have to have you guys rely on it. Me just telling you what it is in my head. I can actually show you what I'm doing, right? It's probably a good idea. Even though if you had the unit circle memorized, I could just say it aloud and you'd be like, oh yeah, sure, of course. Wrong spot. Right? How many of you have memorized the unit circle yet? Just on accident. Man, that's okay. All right, so I'm looking for places where the x-coordinate is -1. The nice part is, because we're going from 0 to 2 pi, I'm just taking one full loop around. The only place where I see that happening is here at pi. You guys agree? Jacob? Yeah, of course. And then the other one, cosine inverse of +1. So again, I'm going to go look for the place on the unit circle where cosine is +1. That happens here at 0. Does it happen again at 2 pi? Yeah, but do I care? Why not? Yeah. Whew. That's a SOG, a son of a gun right there. Note that if this had been 0 to 2 pi with the bracket, we'd have a third answer there, right? That's just a hypothetical. That's why I did it in green. Everybody's okay with the y's? The bracket versus parenthesis made a big difference there on the thingamajigs. Okay. Let's do another. Let's do that's two. Oh, ouch. You know? All right. 3 tan squared x equals 1. What do I have to do first here? Divide by 3. Cool. Then what? Then we'll square root both sides. Good. What do we have to remember? Plus or minus. What's the square root of 1/3? Well, I'm just going to think about it as 1 over square root 3. Everybody's cool with that? Why am I not going to rationalize the denominator? Because when I go to look this up on the unit circle, I'm looking for y over x. There's no coordinate on the unit circle with a +3 in it. That's why I'm not going to bother to rationalize it, because you have to go back and unrationalize it to do that. Plus, it's not a final answer, so I don't care about anything other than final answers being rationalized. So let's break this off into 2 pieces. So I have where tangent x is +1 over root 3, and where it's -1 over root 3. So I'm going to go through here and look for all the places where the y-coordinate has a 1 in it, and the x-coordinate has a root 3 in it. So there's one spot. There's 2 spots. Oops. There's 3 spots. And there's 4 spots. that cool with you guys? All right, get ready. Hold on to your butts for this one. Two cosine squared x plus cosine x equals 1. What should I do first to solve this? Well,
Whoa. Get that solved.
ha! You're funny, dude. What do you guys think? Any bright ideas here? What does this kind of look like to you? What if I write it this way?
Factor.
Yeah, this is a quadratic equation, isn't it? So we got to start by getting it equal to 0 and then either trying to factor it or use the quadratic formula. Boy, that's just mean, Mr. Kulik. You get ready. That's not, we haven't even seen mean yet. All right. Who remembers how to factor something like this? Since it is, I know it is factorable, so we're going to give that a shot. Yeah, Blake?
Well, don't you just like split it up? Oh, yeah, okay, so like the actual factoring. So it's two things that add together to get 1 and multiply together to get -2, right?
Good. So because the leading coefficient isn't 1, you need the two things that multiply to give first times last. And then add to get the middle. So what are those two numbers?
2.
Good. What do we do with those two numbers?
You split the cosine up, so it's 2 cosine x and then -1 cosine x.
Good. So notice here that we've replaced the 1 cosine x with 2 cosine x minus cosine x, which still, when you add them together, gives you 1 cosine x, right? So we haven't really done anything other than like written it in a goofy way, but it still has the same value as the original. We're going to make two groups. In between those two groups, we must have a subtraction symbol, which is why I wrote plus a -1 cosine x instead of minus cosine x. From the first group, we look for a greatest common factor. What's the greatest common factor there?
2 cosine.
2 cosine x. Those variables matter. Which leaves me with cosine x plus 1. Everybody good there? Yep. From the second one, what do we get? What's the greatest common factor? -1, which leaves me with cosine x plus 1. I notice now that each of these factors has a cosine x plus 1 in it. So if I factor that out, I'm left with 2 cosine x minus 1. So this coming back to us, this long factoring technique. We learned it last year, or maybe earlier. We did it a lot, or some of us maybe not enough. Then we can, now that we've got it factored, we can apply the zero product property and set each of these factors equal to 0. So for the first one, I'm finding the cosine inverse of -1. And for the second one, I'm finding cosine inverse of 1/2. Everybody good with that? I go to my unit circle. Cosine inverse of -1 happens at pi. Cosine inverse of 1/2 happens at pi over 3. And then again at 5 pi over 3. Again, because I'm going between 0 and 2 pi, so I'm just looking once around the unit circle. Woo! Doggy! That was a good one, Mr. K. All right, well, let's do one more and call our quits. Sound good? Okay. You thought your mind was blown before? Get ready. So here we have sine 2x equals 1/2. What's different about this one than any of the previous ones? Sure, the sine, but the 2x, the 2 attached to the variable inside the trig function, that's new. That presents a new distinct challenge we'll talk about in a minute. So you probably would say, okay, well, I'm just going to do sine inverse of both sides. And then we'll go to the unit circle and pull out the places where the y-coordinate is 1/2. So that's pi over 6 and 5 pi over 6. And then divide both sides by 2 or multiply by 1/2. And this should be our answer, right? Unfortunately, we've missed some. Oh no. So this is the way that I like to think about it. So going from here, we have 2x equals pi over 6 plus 2 pi n. And then 2x equals pi over, or 5 pi over 6 plus 2 pi n. I'm going to write the infinitely many answers version. Everybody's okay with that? And then when I divide both sides by 2, or multiply by 1/2, this becomes pi over 12, but it also applies here at the 2x plus n, and becomes pi plus n. So now I'm getting another answer instead of every 2 pi, it's happening every 1 pi. Oh, Mr. Kulik, you are a dastardly dude. I know. So when I do that, I have pi over 12, 13 pi over 12. If I added another pi, it would be too big. And here I have 5 pi over 12. And then 17 pi over 12. If I add another pi, though, it would be too big. Notice here that I'm getting 4 answers instead of 2.
Wait, so are you shortening down why are you taking out the pi and the 2 pi?
What's up?
Why are you taking out the pi and the 2 pi?
Because I'm dividing, when I divide both sides by 2, I have to divide everything by 2.
No, but your final answer doesn't include that.
Well, because we're solving from 0 to 2 pi.
So then why does the 2 pi end there?
Well, because
Why did we do that if it's
because I kept adding pi until I got something that was too big. If I add pi again, I'll have 25 pi over 12,
now that makes sense.
which is too big. If I added 2 pi to the other one again, 29 pi over 12, too big. That's why I stopped there. These ones are the sneaky jerks, right? And just, excuse me, guys. Again, I heard some of us saying, oh, it just means you have to go 2 times around or whatever, which is fine until you get something like, what if it was like 5 over 2x? You know, or like, what does that, what the heck does that mean then, right? So like, now all of a sudden, doing it this way where it's purely numeric, and it's just like, okay, this is my new coterminal check, and just keep adding until it stops working, or subtracting until it stops working, depending on what your interval is. Makes a big difference, right? This is nice because it's the same, regardless of how yucky the numbers get. You know what I mean? Okay.